Hi everybody, this is Mr. Scop here. I'm going to show you a couple things. We're going to get back to some math and some mole problems for the gas unit. So I'm going to show you a couple of things on how to be successful with some of these problems. First off, for gas particles, one thing you need to know here as you jot down these notes with me is that just like liquid or solid particles, they're different sizes. So if I took a look at, say, helium, which you remember from last unit is a noble gas, has a small atomic radius. Whereas if you look at hydrogen, you may remember from last unit, hydrogen is going to have a bigger atomic radius. Now the strange thing about gas particles is if I have 1 mole of those gas particles, you remember how many that would be. Of course you do. I know Rosalind probably remembers. Jackson maybe. So you got 6.02 times 10 to the 23rd of those particles. And of course they don't weigh the same if I had 6.02. The hydrogen versus the helium, even though this one is smaller in atomic radius, you know it's got more protons and so forth. Remember, it's got 2 protons and an atomic mass of 4.0026, whereas hydrogen has 1 proton and an atomic mass of 1.00079. So we remember if we have a mole of these guys, hydrogen is going to weigh about a gram, whereas helium would weigh about 4 grams. Probably the most interesting thing about the gas particles is if I had 1 mole of them, they would occupy the same amount of space. Assuming the temperature of both gases and the pressure were the same or constant for both gases. So that's kind of revolutionary right there, in that even though they weigh different amounts, they're different sizes, if I had this many of them, 602 sextillion, they would occupy the same amount of space, assuming the temperature and the pressure were constant. How much space would they occupy? Question mark. Well, the answer is you have to state a temperature and a pressure. So we call, as chemists, we call STP. And what that stands for is standard temperature and standard pressure. So that's kind of a universal thing, whether you're in Russia, Africa, STP, standard temperature, standard pressure. Standard temperature is 0 degrees Celsius. All right. We're going to learn later that is also equivalent to 273 Kelvin. All right, but not to panic. You guys are familiar with the Celsius. And standard pressure is 1 atmosphere. So that's the pressure if you were at sea level, standing on the ocean in San Diego or something like that. That's the pressure that you would feel. At Rolling Meadows High School, if you were to look on a map, we're at an altitude, and this is probably too much information here, of about 550 feet above sea level. So since we're a little higher, our pressure is only about 0.98 atmospheres. All right? But we're going to assume that we're at STP, standard temperature and pressure, for most of the problems when we're calculating. All right? Now, what does that mean? Getting back to our question, how much space would they occupy? Each gas would occupy 22.4 liters. And in fact, if you look up front, there's a black box that's in front of the computer, and you'll notice the label on that box is 22.4 liters, so that you can get a reference as to how big that is. Even more amazing, some of you might remember that hydrogen is actually a diatomic. So, you know, it might even be like this versus helium. All right, and this being bigger molecules here. Even if it was a diatomic, each gas would still occupy 22.4 liters if I had a mole. 6.02 or 602 sextillion of these molecules and helium. Now the reason that each of them occupy that amount of space is gases are so small that the difference in size is negligible. And you know about my spelling, so I'm going to probably put negligible. I don't know. That's my best guess right there. All right, so the difference in size. So in other words, what I'm trying to tell you is that these particles are so small, if I were to have another one of the hydrogen, there would be so much space in between the particles, so much space, that the size of them is negligible, so each gas is going to occupy the same amount of space. So if you're trying to get a visual of what I'm talking about, if I were to have two big football players on a big football field, and I were to have a football field over here and let's say two little cheerleaders, there's so much space in between each particle that the size of the person is actually negligible. That's the same with gas particles. So anyway, getting back to our packets, if we could flip now to page, well, there are no page numbers, but if you take a look inside about page 3, you'll see our old mole map. This is the one we used to do, all right, with our, converting from 6.02 and so forth, using the atomic mass. Well, now, our new mole map, if you look on the next page, just adds an element here. So now we're going to be able to figure out the volume of a gas at STP. And you should now know what STP is, standard temperature and pressure. And we're going to use the 22.4 liters into our problems. So we're going to flip a couple more pages here to mole conversions. All right, I'll let you kind of catch up here. And I'll zoom in just a hair so you can see this a little bit better. But basically, if you look at the first problem, if I had 2 moles of iron and I wanted to figure out how many atoms I have, our typical setup would be to multiply by 6.02 times 10 to the 23rd. So that's nothing new. I'll demo here if I had 4 moles of helium, how many helium atoms would I have? We always set that up over 1. Moles of helium go down here. We're going to use the 6.02 times 10 to the 23rd atoms of helium over 1 mole. So basically 4 times 6, and you can use your calculator, is 24. So you're going to get something like 2.4 times 10 to the 24th. Now I don't have a calculator in front of me, but you type that in and just double check atoms of helium. Now that's nothing new, but you're going to get to problems where you've got to use the STP value of 22.4 liters. So let me show you one of those and then I'll give you some time to work with some partners. So number 5 here, if a mole of neon gas occupies 22.4 liters when measured at STP, then what would I have if I have 2.71 moles? So it's not very challenging. You don't have to worry about it too much, but I'm going to take 2.71 moles of neon, put that over 1. Moles of neon go down low. All right. Now you remember from what we just learned, 1 mole of neon would occupy 22.4 liters. So if I had 2.71 moles, I would simply just multiply those two numbers. And let me grab my calculator here. So I would take, I don't know how well you can see that with the glare, 2.71 and multiply by 22.4. And I would get 60.7 liters of neon. So that's how much space 2.71 moles of neon, assuming I'm at STP. Alright, so it's not that tricky. It's just going to be like riding a bike with the mole problems. You'll be back at it. So what I'd like you to do now is try some problems, and good luck. Email me with any questions.